Total dynamic head. In video 4, we calculated dynamic head for the suction and discharge side of a pumping system. In this video, we will perform pump calculations to find the net effect of the dynamic heads across the whole pumping system. The net effect of discharge and suction dynamic heads is called total dynamic head. Calculating total dynamic head involves adding the net effect of the four heads the pump has to overcome on the suction side to the net effect of the four heads the pump has to overcome on the discharge side. The four heads being static head, pressure head, velocity head, and friction head. This involves a different formula for a suction lift scenario compared to a suction head scenario. This is because static suction head in a static head situation assists pump performance, and in a static lift situation, static head opposes flow to the pump. Total dynamic head with static suction head. As total dynamic head is the total pressure a pump must produce to move liquid from a source to a final destination, and dynamic suction head aids pump flow, then for a pump with suction head, total dynamic head equals dynamic discharge head minus dynamic suction head. Example 1. In the pumping scenario shown, what is the total dynamic head if the suction tank is open to the atmosphere, suction friction head is 0.5 meters, suction velocity head is 1.6 meters, discharge friction head is 1.6 meters, discharge velocity head is 2.8 meters, the destination vessel is pressured to 250 kPa gauge. The liquid is water at 4 degrees C. Okay, here's our example. We have our pumping system drawn. We see it's dynamic suction head, so total dynamic head will be dynamic discharge head minus dynamic suction head. So we're going to divide the problem into 3 steps. First, we're going to calculate the dynamic suction head. Second, we're going to calculate the dynamic discharge head. And then we are going to find the resultant of both heads. Step 1, calculating the dynamic suction head. Dynamic suction head equals static suction head plus pressure head plus velocity head minus suction friction head. Because we are calculating the pressure head on both sides of the pump, we can work in absolute pressure values or gauge pressure values. For this problem, we will use gauge pressure. Static suction head is going to be from the center line of the pump up to the top of the liquid level, which is 5 meters. Static pressure head, suction pressure head equals vessel pressure in kPa divided by the relative density times G. Suction pressure head, because we are working in gauge pressure values, will be 0 kPa, so our suction pressure head will work out to 0.0 meters. Suction velocity head we were given as 1.6 meters. Suction friction head we were given as 0.5 meters. So dynamic suction head will equal 5 meters plus 0 meters plus 1.6 meters minus 0.5 meters. Dynamic suction head works out to be 6.1 meters. Step 2, calculating the dynamic discharge head. Static discharge head, from our diagram, center line of the pump up to the top of the liquid level is 10 meters. Discharge pressure head. Pressure in the vessel, discharge vessel, is 250 kPa. Discharge pressure head equals vessel pressure divided by relative density times G. Discharge pressure head equals 250 kPa divided by the relative density of 1.0 times 9.81 meters per second squared. Discharge pressure head 25.5 meters. Discharge velocity head we were given as 2.8 meters. Discharge friction head we were given as 1.6 meters. Dynamic discharge head equals static discharge head plus discharge pressure head plus discharge friction head plus discharge velocity head. Dynamic discharge head equals 10 meters plus 25.5 meters plus 1.6 meters plus 2.8 meters. Dynamic discharge head works out to 39.9 meters. Step 3, calculating the total dynamic head. Because it's a suction head situation, we have total dynamic head equals dynamic discharge head minus dynamic suction head. Total dynamic head equals 39.9 meters minus 6.1 meters. Total dynamic head equals 33.8 meters. In a suction head scenario, the static suction head, the suction pressure head, and the suction velocity head push liquid into the pump, and the greater its value, the less work the pump has to do, and the less the value of the total dynamic head. So for our total dynamic head with suction head, if the suction friction head was greater than the sum of the static suction head, pressure head, and velocity head, the net result would be a negative number and the pump could not pull liquid into its suction. Since the static head, the pressure head, and velocity head all act to push liquid into the pump suction, this is an unlikely scenario. Total dynamic head with static suction lift. With suction lift, since both dynamic suction lift and dynamic discharge head resist the pumping action and add to the head pressure required, then in a static lift scenario, total dynamic head equals dynamic discharge head plus dynamic suction lift. Example 2. In the pumping scenario shown, what is the total dynamic head if the source tank is open to the atmosphere? Suction friction head is 0.5 meters. Suction velocity head is 1.6 meters. Discharge friction head is 1.6 meters. Discharge velocity head is 2.8 meters. The destination vessel is pressured to 200 kPa absolute. The liquid is water at 70 degrees C, and we are going to use absolute values for calculating equivalent pressure head. So here's our suction lift scenario, and again we're going to divide the problem into 3 steps. First, we're going to find dynamic suction lift. Second, we're going to find dynamic discharge head. And third, we're going to find total dynamic head. So let's have a look at step 1. Static suction lift is from the top of the liquid level in the suction tank up to the center line of the pump, which is 6 meters. Suction pressure head. The tank is at an atmospheric pressure, so suction pressure equals vessel pressure divided by relative density times G. So we have to find the relative density from steam tables at 70 degrees C. VF for water is 1.0228. Relative density equals 1 divided by 1.0228. Relative density equals 0.978. Suction pressure head equals pressure in the vessel, which is atmospheric pressure, 1.01.3 kPa, divided by the relative density, 0.978, times G, 9.81 meters per second squared. So the suction pressure head is 10.57 meters. Suction velocity head we were given as 1.6 meters. Suction friction head we were given as 0.5 meters. Dynamic suction lift equals static suction lift plus suction friction head minus suction velocity head plus suction pressure head. Dynamic suction lift equals 6 meters plus 0.5 meters minus 1.6 meter plus 10.57 meters. Dynamic suction lift equals minus 5.67 meters. Because the dynamic suction lift is negative, we have liquid flowing to the pump suction. Step 2. Calculating the dynamic discharge head. Static discharge head. The static discharge head is from the center line of the pump to the end of the discharge boat, which is 5 meters. So we're going the center line of the pump to the discharge boat, 5 meters. Okay, 5 meters for static discharge head. Discharge pressure head. Since the tank pressure is 200 kPa absolute, discharge pressure head equals tank pressure divided by relative density times G. Discharge pressure head equals 200 kPa divided by 0.978 times 9.81 meters per second squared. Discharge pressure head equals 20.86 meters. We were given discharge velocity head as 2.8 meters. Discharge friction head we were given as 1.6 meters. Dynamic discharge head equals static discharge head plus discharge pressure head plus discharge friction head plus discharge velocity head. Dynamic discharge head equals 5 meters times 20.86 meters times 2.8 meters times 1.6 meters. Dynamic discharge head works out to 30.26 meters. Step 3. Calculating the total dynamic head in a suction lift scenario. Total dynamic head equals dynamic discharge head plus dynamic suction lift. Total dynamic head equals 30.26 meters plus a minus 5.67 meters. Total dynamic head equals 24.59 meters. In a suction lift situation, if the sum of the suction pressure head and suction velocity head is greater than the sum of the static suction lift and suction friction head, then the net value is a negative number. In this case, a negative value is required to push liquid into the pump suction. Vapor pressure. Molecules of a liquid are constantly moving and therefore have kinetic energy. As liquid molecules below the surface collide with liquid molecules at the surface, the transfer of energy to the molecules at the surface can be enough for them to change state and become a vapor. This happens below the boiling temperature of the liquid and is called evaporation. The pressure exerted by the vapor present above the liquid surface is known as vapor pressure. As the temperature of a liquid increases, the number of molecules transitioning into a vapor also increases, therefore increasing the vapor pressure. If the temperature of the liquid keeps increasing, eventually the vapor pressure exerted by the vapor will equal the external pressure exerted on the liquid, and the liquid will boil. When the liquid is boiling, not only are surface liquid molecules changing state, but all molecules throughout the entire liquid will change into a vapor. The values for the boiling pressure in kPa, also called the saturation pressure of water at different temperatures, can be found in the Pan Global Academic Supplement Steam Table number 2. Column 1 lists the temperature of the water and column 2 the corresponding absolute saturation pressure. If the pressure in a pump suction is allowed to fall to the saturation pressure, the vapor pressure exerted by the water will equal the pressure exerted on the liquid, and the liquid will boil or cavitate in the pump suction. For example, at 7 degrees C, water will boil at an absolute pressure of 31.19 kPa. If water at 70 degrees C were allowed to drop to an absolute pressure of 31 kPa in the pump suction, the water vapor pressure would equal the external pressure in the pump suction, and the water would boil. So the suction pressure of a pump must always be greater than the vapor pressure exerted by the liquid at any given temperature.